Hello, my name is Victor. I am a senior quantum control engineer at Q-Control. I specialize in quantum computing, but in particular quantum sensing and quantum bioimaging. Today we'll have a look at making cold atom sensors more robust to noise. So why cold atom sensors? Well, they are incredibly sensitive to gravitational fields and changes of inertial reference frames such as rotation. They have tight bandwidth, excellent long-term stability, which means that in contrast to classical sensors, they do not require external calibration. The application space is diverse and interesting, from precise navigation in GPS-deprived environments to changes in gravitational magnetic fields due to vessel movement or mineral deposits. So let's have a look at how these sensors work. Here on the right, we have a schematic of a vacuum tube. This little sphere in the middle represents a cloud of atoms in a magneto-optical trap, and there are two counter-propagating laser beams used to interrogate it. There is several energy level configurations we can use. In this particular example, we'll focus on the Raman transition, which has two ground states and an excited state, and will move between the two ground states using a highly detuned lambda transition. Now, the key is that while we move from one ground state to the other, here marked with blue and green, we also pick up momentum from the two photons absorbed from each of the laser beams. This is a crucial step that enables interferometry. And we'll see this further on the right. Here we have an image of a space-time diagram depicting a typical experiment. In solid blue, we have a cloud of atoms prepared in a magneto-optical trap. We'll then release this cloud of atoms and let it fall freely due to gravity. And upon release, we'll hit it by a pion 2 pulse. This pion 2 pulse places the two ground states in an equal superposition, except that one of them has now picked up momentum from the photon absorption and is moving faster. So the two sublevels corresponding to each of the states physically separate. So this will give you an indication why this is called a beam splitter. Now we can leave the two subspaces of the cloud falling due to gravity and then hit them with a pi pulse. The pi pulse refocuses the phases as well as the momentum states between the two sublevels. And if we leave them free falling for exactly the same amount of time again, they'll physically recombine. And then if we hit them by another pion 2 pulse, we can recombine their phases as well and measure. Another key aspect here is that the phase imprint that the lasers leave upon the cloud of atoms depends on where the cloud was at the point of interaction with the laser beam. So if the cloud is free falling, that directly encodes the changes in the gravitational field against the k-space of the laser. So in this case, lasers act as rulers, and they imprint the movement of the cloud due to gravity, and this enables interferometry measurements that are highly attuned to gravitational changes. Them being quite sensitive also means that they are exposed to various channels of noise. For example, thermal effects. They, upon release, broaden the cloud so that while it's falling, the cloud of atoms seizes an inhomogeneous profile of the laser intensity, as well as each atom in the cloud having a different detuning due to the Doppler broadening. And then we have a different class of noise, which comes in the form of laser instability. For example, this could be jitter in fiber coupling, which is often present in deployed sensors, for example, mounted on a vehicle. And then we have frequency fluctuations due to mirror vibrations as well. So we'll focus on these two noise channels. Here is a Hamiltonian. Omegas are the two laser drives. Capital delta is the single photon detuning frequency, which we keep large. Small delta is the two photon detuning frequency, which is purposely kept small. Then we have the Doppler broadening channel that describes the spread in momentum across the cloud of atoms, particularly in the z direction. So this is the direction of the free fall and the two counter-propagating laser beams. And then we have amplitude fluctuation channel labeled as B, which determines the changes in intensity of the laser drives. The point here is that we would like to construct a control protocol that suppresses these two noise channels. So the way we'll do this is to use a quantum control toolkit in Q-Control's possession. You can actually see this toolkit and explore it. And if you go to our website called qcontrol.com, as you can see highlighted on the top, and then if you click the sign up button, all you need is an email address and you'll see our products. What I'm showing right now is our entry product called Black Opal, which has some sophisticated capabilities and also advanced visual capabilities. For example, what we see on the screen right now is a segment circuit describing visually a 2-qubit gate, and it's depicting complete entanglement space between the two qubits with ideal and noisy trajectories as well. This is a great teaching tool, and I would actually encourage you to explore it and play around with it. However, for the purposes of this talk, we want the product suite called Boulder Opal. This is a Python library containing sophisticated tools that enable quantum control. Here we see technology guides that describes how to use these tools in various different physical hardware. And you can also click on feature guides, which will guide you through how to set up the system, how to simulate it, how to optimize the system, which is actually what we want in this case. We can have a quick peek. So the notebook that we see here will give an example Hamiltonian, and we'll show you how to set up the system, defining your control channels. So for example, your drive, your frequency shifts, drifts, then noise channels, and then finally pulses that you would like to generate that involve maximum Rabi rates, durations, number of segments, bandwidth limits. Now you have to define the target. So this is a unitary target operator that the control channels collectively will try to achieve. And then with a simple command, our toolkit performs a sophisticated numerical heavy lifting for you and provides pulses that are robust to the noise channels you have defined and achieves simultaneously a high fidelity unitary operation. So let's actually have a look at how this works. We'll go back to the talk, and we'll try to generate a pulse that suppresses these two, so amplitude and Doppler shift channels. In this particular case, we can even make a simplification just to keep things clear, and reduce the system to a two-level Hamiltonian. Why? Well, because the highly retuned lambda transition enables us to focus on the two ground states. The cost that we'll try to optimize in this particular case will be a combination of unitary evolution infidelity and also the filter function component. So the filter function is how we define the response of the controls to all of the noise channels at the same time. And by minimizing this term, we can create pulses that are profoundly robust to a multitude of noise channels at the same time. Here at the bottom, we see the beam splitting pulse and the mirror pulse generated this way. So in this case, they include the phase control and the frequency shift control, but they could have had other controls as well. Let's test how robust these pulses are, just to build up intuition of what is actually happening. So the top row shows robustness to amplitude noise. So in red, we have a primitive square pulse, and in purple, the optimized pulse. And we see that the purple optimized pulse remains highly robust to shifts in laser drive for up to 30% changes in amplitude. Similarly is true here at the bottom row shown for the momentum noise that affects thermal broadening and Doppler shift in these devices. So let us have a look at how they perform. So what we'll do is simulate a detection sequence. We'll prepare the atom cloud, then we release it, we'll apply the beam splitting pulse, evolution, the mirror pulse, evolution, and then measurement. Our lasers that we use for these pulses will have significant noise on them with a Gaussian distribution and a standard deviation 25%. And we'll also have thermal broadening noise that's characteristic of these devices. So let's see how the primitive pulse compares to the optimized pulse. Here, we have a signal. In purple, it's the optimized pulses. In red, the primitive pulses. What we are actually interested in is the gradient of the signal, because this is directly proportional to the sensitivity. And here on the right, we can see the gradient. And in terms of optimized pulses, we can see that it's significantly larger than the primitive pulses. So this is significant because the noise levels we used are quite large, and we can expect similar noise levels in deployed sensors in various environments. So to summarize, we have shown that through carefully optimized quantum control, atom sensors in field conditions can be tangibly improved in terms of sensitivity. With this, I would like to conclude. Welcome you to visit our website, sign up, explore our toolkit, and I would like to wish you all the best and say goodbye. Thank you.